In this video, I introduce the latent diffusion models for high-resolution image synthesis. Diffusion models performed in pixel space learn a data distribution by gradually denoising a normal distribution with a low inference speed and a very high training cost, especially for high-resolution image synthesis. Latent diffusion models conducted on a compressed latent space of a lower dimensionality speed up inference and reduce the computational demands by separating compression of imperceptible details from the generative learning phrases as shown here and here. LDMs use the image X as input. The encoder E encodes X into a latent representation Z, and the decoder D reconstructs the image X delta from the latent Z, namely X delta is calculated from the decoder D. The encoder E downsamples the image by a compression factor F to reduce the amount of information processed in the reverse process. Denoising diffusion models use a sequence of denoising U-net epsilon theta t from 1 to capital T to predict the denoised variant xt of the input X. Using the Gaussian kernel and reparameterization, the denoising score matching objective is defined as here, where T is uniformly sampled from 1 to capital T, and epsilon is a score-based model. Using the trained encoder E and the decoder D, the imperceptible details in the low-dimensional latent space are abstracted away. The objective on the perceptually most relevant bits are defined as here, where ZT is obtained from E during training. The samples from P learned data distribution is decoded to image space with a single pass through this D decoder, this encoder, this denoising U-net, and this cross attention, this generation condition. The conditional generative model P is conditioned on input Y through a conditional denoising autoencoder epsilon theta. A domain-specific encoder tau theta is used to introduce Y to the reverse process to generate a conditional image. The cross-attention is computed by using this formulation and explained in this figure, where this query Q, key, value V, and this phi I is output generated by the model epsilon theta. W, Q, W, key, W, V are learnable matrices. Based on the image conditioning pairs, the conditional latent diffusion models are trained using the following objective as shown here, where both tau theta and epsilon theta are joint optimized. These are some samples from different training data sets. For more details, please check with these references. Thank you.